Jordan, if you dropped a hammer and a feather on the moon, they'd hit the ground at the exact same time. On Earth, we think gravity is predictable, but it's actually the weakest and most mysterious force in the universe.
Wait, the weakest? It literally keeps my feet on the ground and prevents the atmosphere from floating away into space. Explain how that's weak.
Think about it this way: you can pick up a paperclip with a tiny kitchen magnet. That little magnet is successfully fighting the gravitational pull of the entire Earth. Today, we're looking at gravity, from the Latin gravitas, meaning weight, and how it's basically the master architect of the cosmos.
All right, I'm ready to feel the weight of this topic. Let's get into it.
Gravity has been the lead director since the very beginning of the universe. Just after the Big Bang, the universe was basically a giant soup of hydrogen and dark matter.
So it was just a big cloud of nothing much. How do we even get stars out of that?
That's where gravity comes in. Tiny clumps of matter started pulling on other tiny clumps. This pull caused the hydrogen gas to coalesce and condense, eventually getting so hot and dense that it triggered nuclear fusion, creating the first stars.
So without gravity, we don't just lose our footing, we don't even get suns or planets in the first place.
Exactly. Gravity forced these stars to group together into galaxies and clusters. It's a primary driver for every large scale structure we see when we look at a telescope. It has an infinite range too, though it gets weaker the further you move away from an object.
Okay, but who actually figured this out first? Because for a long time, people just thought things fell because they wanted to be on the ground.
For the longest time, we relied on Isaac Newton. In the late 1600s, he gave us the law of universal gravitation. He calculated that every object in the universe attracts every other object, and the strength depends on their mass and the distance between them.
Newton's the apple on the head guy, right? That formula worked for a long time.
It did. And honestly, for most things on Earth, Newton's math is still all we need, but it didn't explain everything. It couldn't tell us how gravity actually worked, just that it did. The real game changer happened in 1915 when Albert Einstein published his general theory of relativity. He didn't see gravity as a force pulling on things. Instead, he saw it as geometry.
Geometry, like triangles and circles. How does a shape make me fall off a ladder?
Imagine a trampoline with a bowling ball sitting in the middle. The ball curves the fabric of the trampoline. If you roll a marble nearby, it's going to roll toward the bowling ball because the surface is curved.
So the Earth isn't pulling me, it's curving the space around it, and I'm just sliding down that curve.
Spot on. Einstein proposed that mass and energy actually warp the fabric of space-time. The more mass an object has, the deeper the warp.
That sounds like it could get pretty extreme. What happens if you have way too much mass in one spot?
You get a black hole. That is the ultimate expression of gravity's power. The space-time there is so curved and so steep that not even light, the fastest thing in the universe, can climb out once it passes a certain point called the event horizon.
That's terrifying. But back on Earth, things are a bit more stable. Gravity here seems pretty consistent, right?
Mostly, but it's actually modified by the Earth's rotation. The centrifugal effect from the Earth spinning actually slightly counteracts gravity at the equator. You actually weigh a tiny bit less at the equator than you do at the North Pole.
I'll remember that for my next diet. But even with Einstein, do we finally have the whole picture?
Not even close. This is the biggest active problem in physics right now. We have two sets of rules: general relativity for the big stuff like stars, and quantum mechanics for the tiny stuff like atoms. But they don't play nice together.
They don't match up. Why not just use Einstein's rules for the tiny stuff?
Because when you apply Einstein's math to atoms, the numbers turn into nonsense. Scientists are currently hunting for quantum gravity. They want to find a theory of everything that links gravity to the other fundamental forces, but so far, gravity is refusing to cooperate.
While the physicists argue over the math, how is gravity actually affecting us right now, besides the obvious keeping us on the planet thing?
It runs the planet's systems. Gravity moves the moon, which in turn creates the tides in our oceans. It dictates weather patterns by moving cold and warm air masses around.
Does it affect life itself, like biologically?
Absolutely. Plants use gravity to know which way to grow. It's a process called gravitropism. Roots grow down because they sense gravity's pull. In humans, our hearts have to be strong enough to pump blood upward against gravity to reach our brains.
So if we went to a planet with double gravity, our hearts might just give out because they aren't built for that much work.
Exactly. Our bone density and muscle mass are all calibrated to this specific 9.8 meters per second squared pull of Earth. We are literally carved by gravity.
It's weird to think of a force as a sculptor. It feels like this invisible hand that's just everywhere.
It is. From the way your coffee pours into a mug to the way the Milky Way spins, it's all the same interaction. It's the universe's way of making sure everything stays together.
All right, Alex, We've covered space-time warps and plant roots. What's the one thing to remember about gravity?
Gravity isn't just a force that pulls things down, it's the physical warping of space and time that creates the structure of everything from our bodies to the farthest galaxies.
That's heavy, no pun intended.
That's Wikipedia, every story on demand. Search your next topic at wikipedia.ai